if a sample of 3 batteries is selected from a lot of 10, of which 2 are defective, what is the expected number of defective batteries? So we're looking for, if we pick 3 batteries out of this group, on average, how many batteries are going to be defective? So there's a long way of doing that, and there's a short way of doing that for this particular circumstance. Most of the time, and most of the circumstances, you're going to have to do the long way, where you say, okay, I'm going to let x be the number of defects, which means that x can be from 0, 1, or 2. Yeah, I'm picking 3 batteries, but I know that out of this lot of 10, there's only 2 that are defective. So, I can't have x being 3 because, essentially a probability distribution, if I put 3 there, I would say, well, there's no chance of that happening. Well, I usually don't allow anything on my probability distribution that would have a 0 probability of happening. So how would I calculate these? Well, kind of going back to the way we did it before. This one's saying, okay, the probability of no defects, which means all 3 of them were good batteries. Which means that when I chose my 3 out of 10, I'm choosing 3 out of the 8 that were not defective. And that gives me 0.4 repeating 6, which is basically 7 out of 15. Same thing for 1, is I'm going to calculate that, but now, I'm going to have 1 defective. So I'm going to have basically 2 that are not defective and 1 that is. So when I do that probability, I'm going to have 2 out of the 8 that were not defective. I'm going to have 1 out of the 2 that was. So multiply those together over, again, me choosing 3 out of 10 batteries. And I get another 0.46 repeating, which is another 7/15. Now, I could do the formulation for this, for 2 here, which I could say, okay, well, I'm going to have, C of 8, 1 times C of 2, comma 2 for that over C of 10, comma 3. Or I could realize that if I add these together and take that total from 1, I get 0.06 repeating, which is basically 1/15. So now I have each probability, and for each number of possible defects in this choices of mine. So now I'm able to do the expected values. So I'm going to take each one of these x's and multiply it to its probability. And then I'm going to add them together, and I get a total of 0.6 defects. Which means on average, I'm going to have 0.6 defects. So that means probably somewhere between 0 and 1, kind of starting to lean towards the 1. So I have an okay possibility of getting a defect out of 3. I'm probably not going to get 2, but most of the time, I'm going to expect probably 1. But getting 0 is not unheard of either. Now, the short way for this particular circumstance depends on the context you have of this. So the easier way for this circumstance, now again, the previous one is what you have to do most of the time. This one here, if you happen to look at this, say, okay, well, I'm choosing 3 batteries. I know that 2 out of 10, or 0.2 of them, are defective. So if I have 3 batteries times my probability of 0.2, I do get 0.6. So that's another way to come up with the expected value. Is I know how many batteries I'm choosing. I know on average what the probability of getting a defective battery is. Now, is this entirely accurate? It's kind of hard to say because of the fact that technically I'm choosing these batteries without replacement. I'm not going to say this is the battery, this is the battery, and this is the battery, and point to the same battery all 3 times. Then I would have a possibility of having 3 batteries that are defective if I did that. So, but for this circumstance, I know the overall probability, because we're saying it's a 2 out of 10, are defective on average. And basically, so you're kind of using more averages here to do that. So because of this circumstance, you can get away with it. But as I said, the easy way for this doesn't work in all circumstances accurately. So the way I showed at first, the long way, is the way you should probably go most of the time to be accurate.